Chapter 11 is about intermolecular forces and the way that they control why the states of matter behave the way that they do. We just covered the section on, oh, look at that, blank screen. We just covered the section on solids, and so now we are continuing that conversation with liquids. So here we go. You've had before, when we've talked about states of matter in physical science, we've talked about the fact that liquids, you know, they fill their container and things of that nature. They're porable, they're fluid. We're going to get into a little bit more detail with the nature of liquids here in chemistry than you have before. We're going to talk about some of the unique properties of liquids that are different than gases. They share many of their features with gases, but not all of them. Cohesion is something that we talk about when we talk about liquids. Cohesion means that molecules are attracted enough to each other to stick together. Now, in a gas, they have so much thermal energy, they're moving so fast that when they run into each other, they just bounce off and keep going, kind of like people in the New York subway, right? They run into each other and they don't even bother to say, excuse me, because that's just what happens in the New York subway. And you keep walking and you bounce off each other with no attraction, right? But in liquids, they don't have as much thermal energy. They're not traveling as fast. So their interactions are long enough with each other to stick. And so they bump into each other and then they slide past each other instead of ricocheting off and keeping going about their day. And so the molecules of a liquid, they cohere, they stick together. Different liquids stick together with differing amounts of cohesion, and that has to do with the intermolecular forces. So polar substances tend to have more cohesion than non-polar substances, and polar substances tend to be liquids at higher temperatures than non-polar substances because they're more attracted to each other. If the best thing they've got going are those London dispersion forces, then they stick to each other, but not very well, and they tend to very quickly become a gas. Okay, so cohesion means they stick to each other. Surface tension. This is that weird thing called a meniscus at the top of a liquid. Have you ever noticed when you're measuring a liquid, it could be something scientific with a graduated cylinder in this class, or it could be a measuring cup at home when you're making something and you need a certain amount of oil or water in the measuring cup. But when you look at a liquid through a clear container and you see the surface of the liquid, the surface of the liquid looks thicker than the rest of the liquid. Have you noticed that before? You ever noticed that when you're measuring something? Yes? Yes? And it usually has a shape. Sometimes it bows up in the middle, but more often than not, it bows down in the middle. And it looks kind of like a lens on the surface of the liquid. And that barrier is called a meniscus, and the phenomenon is called surface tension. Molecules along the top of a fluid hold tighter to each other than molecules elsewhere in the fluid. It's like down in the fluid, they all are running into each other and they're all friendly, and so they all slide past each other and it's all good. But then when the molecule happens to wander to the top of the liquid, all of a sudden it's exposed to the air. It's exposed to something other than itself. It's like, ooh, I don't want to touch that. And it gets back down to the bottom. So it like grabs its friends a little closer, right? Imagine you've gone out and seen a movie with your friends and you're walking out of the Consolidated Theaters at Pearl Ridge and it's 11 o'clock at night. And you're all friends, you saw a movie together, so you're walking together. But then you see some, like, I don't know, dangerous looking people lurking in the shadows, and it's 11 o'clock at night at the mall. And so all of a sudden you're like, ooh, you all kind of like clump, and you walk past them, and you spread out again. Now, it has nothing to do with dangerous molecules, but it's that same phenomenon where molecules are sliding past each other with a certain amount of cohesion. But when they come up to the surface, and there's different molecules up there, they're like, ooh, I don't know if I want to touch you. And they grab tighter to each other. And the tension, the cohesion between molecules on the surface is stronger than the cohesion between molecules down in the body of the fluid. So that thing that it forms, that like film that it forms, is called a meniscus. Okay. Chemicals which disrupt surface tension and break up the meniscus we call surfactants. And so you can see the word surface there. And so they're messing up the surface, and they are active. They're active on the surface. They do something to the surface. It's called a surfactant. I am out of Kleenex, and I apologize. Oh no, look, just in the light. I don't need a light. Here you go. There you are. So chemicals which disrupt the tension are called surfactants. Those are usually used chemically for soaps. Soaps tend to disrupt surface tension, which makes things like oil particles easier to break up and wash off of your keister. Okay, so we use soaps frequently for that. So again, liquids tend to adhere to each other, and you can see that these droplets are still liquid molecules trying to stick together. And as they're forced upwards, they do their best to still stick together. They don't like turn into a mist all of a sudden when they're disrupted. They still grab each other. They still have that cohesion. And here on this dew on grass, you can see the water isn't laying flat on the grass. It wants to stick to itself. And so it forms these dewdrops, these balls of water on the grass, because they're sticking to itself. And yes, it sticks to the leaf. You can see them, dangling on the leaf, on the bottom of the leaf. But more often than not, they try the best they can to just stick to themselves. And that's why they make little, lumps of water instead of spreading out flat, like you would imagine a liquid would do. Okay? The surface tension allows bugs to walk across the surface of the water. If you've ever seen water striders. These are bugs, and this isn't necessarily nasty, slimy water that's thick and full of goo. This is just water, and the tension, the surface tension provided by water molecules grabbing each other at the surface is strong enough that if a bug can spread its weight out around a lot of that water, then the water will actually hold his weight, and they can walk across the surface of the water. So, Jesus did not spread his weight out around the water. There are lizards, yeah. But even then, people do that. It's called swimming. Yeah. There is a lizard that the nickname of it is the Jesus Christ lizard, because it can run across the surface of the water. But it doesn't necessarily use the surface tension. It has toes that make air pockets that it like stands on as it goes across. But still, surface tension is cool. This is a little video that I will show you in 1 minute and 57 seconds. How many drops of water can you fit on a penny? And it's just a neat demonstration of surface tension. So they just start dropping water on there. And you can see how the water stands up, because it doesn't really want to stick to the penny, it wants to stick to itself. And so you can put a lot of drops of water on that penny, and the water isn't laying flat. Liquids are supposed to take the shape of their container and lay flat against the bottom. And so you'd imagine the water just runs off the penny. But you can actually put a lot of drops of water on there and get quite a tall mountain of water before the water decides to run off. And then they shake the table to show that it's actually quite stable. The water is glued to itself and would rather stick to itself than run off of the penny. So you can add more, and eventually the mass of the water on top of the penny is going to be too much, and it'll spill off and run down onto the table. But it's astounding how much water just sits on that penny, and that's because of the surface tension and the cohesion of water. Okay? And if we, that's not too much further. There you go. Now the surface tension finally had to give way to gravity, and it ran off. Okay? Oh, just kidding. This next one's really cool. This is a young man demonstrating surface tension.
Did you show me how to make a boat? and it's propelled by soap. First, you need a piece of cardboard, and then you draw the boat on the cardboard. Make sure that the boat will have an opening at the back. That's where the soap will be coming out. I'll cut your boat out. This is how it will look like. And now we're going to put some soap right here where the opening ends. And the soap will be like this. I put the ball gently on the water and then watch it go. You make two boats and have a boat.
Isn't that fun? So this is your lab. Yeah. No. And what's happening there is the soap is a surfactant. It disturbs the surface tension, and then as the surface tension is leaving, it makes a very small wave, and that little wave, as the surface tension is being broken down, is enough to push the boat forward. So the boat is surfing on an itsy bitsy wave of the surface tension being destroyed by the soap. It's kind of cool. There you go. Viscosity is another term we want to talk about. It's a liquid's thickness. The higher the viscosity, the thicker the liquid is. Highly viscous substances are thick. Lightly viscous substances are thin. And so think of like honey or motor oil or Vaseline as being highly viscous. They're thick. They're sometimes sticky, but it doesn't have to be sticky. It just has to be thick. Low viscosity means that the liquid is very thin. It pours fast. Think of like rubbing alcohol. That pours really quickly and doesn't pile up very much. Okay, so viscosity means the thickness of a liquid. That's just a term that we measure that property of liquid with. Adhesion, molecules of a liquid can also stick to other substances, and we saw that with the water on the penny, right? The water was sticking mostly to itself, but when you shook the table, it didn't immediately jump off of the penny. It did also stick to the penny. And the drops of water on the leaves that I showed you, they are sticking to themselves, but they're also sticking to the leaf. There are drops of water on the bottom side of the leaf. So liquids can stick to themselves, that's cohesion, and liquids can stick to other things, that's adhesion. And we use adhesion when we talk about adhesives, like glue, that sticks things together. So adhesion means to stick to something else, cohesion means to stick to yourself. Capillary action, this is the tendency of a liquid to move up a narrow tube because of cohesion and adhesion. So the way this works is you have a little small thin tube, and you dip the bottom of the tube in liquid, and the liquid sticks to the side of the tube and to itself. And so as it's sticking to the side of the tube, it's like attracted to the tube, and as it comes up against the tube, it pulls some water up against it. And then it says, oh, I can go higher now, and it sticks itself to the wall of the tube and pulls more water along with it. And as long as the tube is very, very, very small, the water can actually climb the tube without you needing to like suck on it or anything like that, because it sticks to itself into the tube enough that it just goes up the tube. You can notice this with clear drinking straws. If you just put a straw in a glass of water, the water level inside the straw will be slightly higher than the water level in the glass. But the straw is too big around to get too much capillary action. So the capillary action just raises the water a little bit in the straw, but the water inside the straw will always be a little higher than the water in the glass. Okay? And that's because of capillary action. So here, let me show you some pictures. If water sticks to filter paper, then that's adhesion. If water sticks to itself, that's cohesion. There's just a dumb little picture that might help you remember those two things. You can think of co like company or cohort. Co usually means the same sorts of things, right? Comrade, It means two things of the same nature. Add means different. So that's how those words come to mean what they are. When you pour a glass of water, if you pour too slowly, it runs down the glass and drips out the bottom. Anybody ever had that happen? You're like, I over poured myself a glass. Let me share some with you. Let me have your glass. And I'm going to pour it here. But instead of pouring it into their glass, you pour it on the table behind you. And that's because of adhesion. The water comes out over the top, but you haven't poured it hard enough to make it leave the cup. So gravity says go down, and the cup says stick to me. So it goes down along the bottom of the glass, and you wind up making a big mess, right? So that's an example, again, of adhesion. This is capillary action. All of these cylinder tops are open. All of the air pressure is uniform, and fluids like to seek their own level. So you would think that a U-shaped structure with tubes all open at the top and a reservoir connecting them, that all of the water levels would be the same going across. But they're not, because as the tubes get smaller, capillary action becomes a factor, and the water actually rises a little higher in the smaller tubes. And in this very narrow tube, it's quite a bit higher than it is in the big tube. And then it's not like there's more pressure there. It's just that capillary action is drawing it up. Okay? There's that. And then the last thing, surface tension of meniscus, and this actually should have been in the first set of pictures. But you can see if adhesion is strong, then the meniscus is bow-shaped. The substance would rather stick, would like to stick to the side just as much as it's sticking to itself. So the side draws it up, and water has this downward bowing meniscus. But mercury is a liquid and really doesn't like to stick to anything. Mercury runs off of anything that it's on. And so it has very low adhesion. Mercury has a convex meniscus. It bubbles up in the middle because it's trying not to touch the tubes of the walls of the tube. And so very low adhesion. You get an upwards sloping meniscus. High adhesion, you get a downward sloping meniscus because it's liking to stick to the walls of the tube. Phase changes. Phase changes. Phase change 2.0. We have talked about phase change so many times. You're like, oh my goodness, really phase change again? We did this in second grade. Yes, you did. But we're going to add some new terminology to it, and we're going to talk about more of the why this time around. So liquids going to gas, we've called that boiling before. Because if you put a pot of water on the stove, like I did this morning when I made tea, and you turn the fire underneath it, the water gets hot and gets hotter and gets hotter, and eventually the water boils. And it's starting to turn into gas. But we're going to use a new word now. We're going to use the word vaporization to talk about any time that a liquid turns into gas. Because there's actually two ways that can happen. That can happen because of high temperature, which is boiling. That's what I did when I put the water on the stove this morning. I boiled the water because I did that with heat. But I can also get liquid to turn into gas at low pressure, at low temperature, just because sometimes random fluid molecules have enough energy that when they hit the surface tension, they pop right through and all of a sudden find themselves as gas. And they're like, whoa, I was a liquid a minute ago, and now gas. And when that happens, that's not boiling. Nobody put heat underneath that thing. That just evaporated. So there's two kinds of liquids turning into a gas. The first one, and both of those generally are vaporization. The first one is boiling because it happens because of heat, and the second one is evaporization because it just happens randomly. Certain particles have enough energy to pop through the surface tension and find themselves as a gas. And you know that this happens too because here in Hawaii it seems like lots of people don't have dryers. We don't have a dryer. We hang our clothes out on a line. And it seems like lots and lots of people here do that too. It's really common. So when you hang your clothes out on a line, you don't then walk outside with a blow dryer and heat them up, right? the sun heats them up, and the water in the clothes just exposed to the air, they dry. And the reason that they dry is because the water randomly gets enough energy that sometimes it pops through the surface tension of the liquid, becomes a gas, and floats away. And the sun does add some thermal energy to that. It's not without the sun. You couldn't do it very well on a cold day at night. But still, it just goes away, and that's called evaporation. Okay? Gases turning into a liquid are condensation, and we've used that word before. Inside a sealed container, vaporized molecules will exist as a gas above the liquid. So, in my flask, my drinking bottle, which I didn't know one of these before I came to Hawaii either. This is a Hawaiian phenomenon to me. I think it's fabulous. But in here, I have some ice cubes and some water, but it's not all the way full. There's some gas above there. And this is sealed, and it has been sealed. And in here, there's water vapor above the water liquid. And the vaporized molecules are floating around as a gas. And inside here, there's a little bit of pressure buildup. Okay, now I haven't opened this bottle all morning up until this moment, knowing that this would happen. Have you guys ever noticed on these sealed hydro flasks, or this one is made by Contigo, whatever, these sealed flasks, that when you open them, sometimes there's a little pop. You ever notice that sound? And you think, oh, it's not boiling in there. Why did the air pressure build up? Has your brain ever asked that question? Or do you just accept that there's a pop when you open the bottle? Okay. I'm going to tell you why there's a pop, even though you don't care. Okay. The pop is there because sometimes these water molecules burst through the surface tension, find themselves as a gas. Now, there's already atmosphere above the liquid. There was already air up there. And so when that water molecule slams through the surface tension and becomes a gas molecule, it increases the pressure above the liquid just a little bit. But over time, enough gas molecules are created above a liquid that we build up something called a vapor pressure. And so inside the flask, there is more pressure than there is outside the flask, because outside the flask, there aren't little water molecules that are deciding to become gas, that are deciding to vaporize. Okay? So when you open it, oh, it was very quiet, but I heard it. When you open it, that gas pressure equalizes, okay? And so that's because of the vapor pressure. Vapor pressure is buildup of pressure because of water, or not, actually I keep saying water, because of liquid molecules that have decided to become a gas molecule, that have popped through as a gas. The higher the vapor pressure, the more likely that some of the gas particles will condense back into a liquid. So as the pressure above the liquid builds up, now there's less and less room above the liquid for these liquid molecules to pop through the surface tension and become a gas molecule. When they do that, they're like squeezed back down into the liquid. And it's like, no, there's no room for you up here. Go join your silly liquid friends, right? And then it gets squeezed back down into the liquid. And so that causes condensation. And there comes a point where the vapor pressure has built up and liquid is turning into gas. And then this point of pressure builds up where no more liquid can turn into gas because the pressure is keeping that from happening. So every time a molecule does pop in, some other gas molecule has to go back into the liquid, has to fall back into the liquid, go through the surface tension, and become a liquid again. And so you get to this point where it's called dynamic equilibrium. It's not like no more liquid is ever becoming gas and no more gas is condensing back to the liquid, but it's happening at the same rate, where there's as much liquid becoming gas as there is gas becoming liquid. And so the exchange is happening at the same rate, and it's called dynamic equilibrium. Okay, so here's a sealed flask. The vapor pressure is the pressure of the vapor on the walls of the container. My liquid is coming out of the liquid and becoming a gas. and bouncing around and creating this pressure in here. Now, if there's no pressure, if there's no seal, if it's not sealed, then the liquid can just go away. And that's what happens if you leave a glass of water on the counter. The water level drops and drops and drops, and if you're really bad about washing your dishes and you leave a glass of water on the counter for like 2 weeks, all of a sudden the glass is dry because all of the liquid has gone out into the universe. But if it's sealed, then that pressure builds up and it can't keep going. That pressure will then force the molecules back down into the liquid, and you get this point of dynamic equilibrium. Okay, here again is a picture of that to help you understand. We've got sealed containers. The molecules are all in the liquid state. Some of them pop through and are turning into gases, but eventually so many of them have popped through that the gases are now also becoming liquids, and the exchange at the surface tension is the same in both directions. Phase diagrams. A phase diagram shows the phase that a substance will take given any particular pressure and temperature. So I'll show you pictures in a minute. They're a diagram that has pressure along one axis and temperature along another, and then they color the region of the graph to show you, will this substance be a solid, a liquid, a gas, a plasma, a superheated liquid, a supercooled liquid, all these different phases that matter can take. And so the diagram helps you predict what a substance will be at a given pressure and temperature. There is on every phase diagram something called a triple point, where a solid, liquid, and a gas can all exist simultaneously. That happens for water in a glass of ice water. Okay? In my flask, again, there's ice cubes, there's water, and there's water vapor above the flask. And the flask keeps the water at its triple point. So there is some solid water, ice, that is melting into liquid, and there's some liquid that is running into an ice cube and freezing to the ice cube. So there's a dynamic equilibrium there. There are some liquid molecules of water hitting the surface tension and becoming a gas, and there are some gaseous molecules that are being squeezed back into the liquid, so there's dynamic equilibrium there. And so at this condition in my flask, I have all three kinds of matter. Every substance, maybe I should be cautious about that. Most substances have a triple point, have a place on the graph where solid, liquid, and gas can all occur. Okay, sometimes there are weird circumstances, things that you will never encounter in your normal existence, but it's there somewhere. The boiling point is where boiling happens at 1 atmosphere. So on a graph, and you'll see the graph in a minute, you find 1 atmosphere and you draw a line across the graph, and the point where that line that you've drawn crosses from the liquid region to the gaseous region, that's the boiling point. Okay, so you'll see that again in a moment with some diagrams. And then there's something called a critical point. And that is the highest temperature and pressure at which a gas can be liquefied. Above that pressure or above that temperature, we can't get a liquid to happen. And we get into things called superheated gases, or sometimes superheated liquids. And these are, or sometimes it's called a critical fluid. But it's strange circumstances you don't normally run into. But you'll see that point on the graph. So let me show you some pictures of these things. This is a phase diagram, okay? And at 1 atmosphere, here's temperature at 0 degrees Celsius and 1 atmosphere, a solid will become a liquid. And this is the melting point. And at 1 atmosphere and 100 degrees Celsius, a liquid will become a gas. What do you think this substance is that I'm looking at? Water. Right, this is water. But notice what a phase diagram tells you. You can boil water at sea level at 100 degrees Celsius. But I used to live at 8,500 feet in Flagstaff. 8,500 foot elevation, not 1 atmosphere of pressure. We have quite a bit less pressure. So when you go down in pressure, water no longer boils at 100 degrees Celsius. You go down in pressure, water boils at lower temperatures. I just wanted to know, because I taught science in Flagstaff, just like I taught science here, I want to know what temperature does water boil at here. So I took a Celsius thermometer, put it in my pot, and made some tea. The water boiled at 91 degrees Celsius in Flagstaff. And so 100 degrees being the boiling temperature of water, not always the case. Because you can see this line is not straight up and down. The boundary between liquid and gas is curved, and the lower the pressure, the cooler it is where the water boils. So you could go to a very low pressure, and water would actually boil at its freezing point. And so these phase diagrams help you see pressure and temperature, and you can predict where you can find what state of matter these substances will take. If you go to very, very, very low pressures, then gaseous water, water vapor, will go straight to solid, and there's no liquid at all, right? And that's called sublimation or deposition. And so that can happen at low pressures. Go very high pressures, and now water boils at a much higher temperature than 100 degrees Celsius. So if you were to take your pot, your tea kettle, and your camping stove, and go to the Dead Sea, which is the lowest point on Earth, and make yourself a pot of tea at the Dead Sea, you would have to boil your water at higher than 100 degrees Celsius, because all of that additional atmospheric pressure would mean that the boiling point of water has gone higher. Okay? This is the triple point. This is where solid, liquid, and gas can all coexist, and it's usually where the liquid phase ends, and it dies out into the solid and the liquid, solid and gaseous. Okay, and then the other point that we talked about was the critical point way up here. The critical point at 374 degrees Celsius and 218 atmospheres. That's very high pressure, very high temperature. Above that pressure or above that temperature, we have something called a supercritical fluid, where you can't really tell if it's a liquid or a gas. And it's really neither. It's this strange state of matter. And so that's the critical point there. Okay? You will be answering questions off of phase diagrams for all kinds of different substances in the next couple of days. And that is the end of it. Any questions? Dynamic equilibrium, the point where things are crossing one direction of this line at the same rate that it's crossing the other direction of the line. So there's no noticeable change. Okay, any other questions? Alrighty, cool beans.